Yes, we're starting recording now, so we're good. We're good. I will have to. Let me look. I do have the defibrillator problem. I wanted to do the defibrillator problem. It just had it stapled to the wrong thing. So last, it would help if I have the right thing showing. Maybe. Okay, you guys see the document camera over in Enid? Thumbs up. Okay, cool. Okay, where we ended last Friday was talking about the defibrillators were one of the things that are out there that we look at as capacitors, and for you medical types or your biotypes, it's a more practical type problem. So we've got a defibrillator that's going to put out 300 joules of energy, and it's going to have a 30 microfarad capacitor. And we want to know what is the potential. So you can figure out what it's like compared to a battery. So if we did it, we looked at our energy of a capacitor. So the energy of the capacitor, which our book is using as a UE, there are a couple of different ways that we can look at this. And I've got my capacitance divided by 2 and my change in potential squared. So when you guys are getting ready to do your test and doing your cheat sheet on your test, you want to have your energy of your capacitors in its various forms. Remember, we could do it in a couple of different forms. So if I'm solving for potential, I'm given energy in the problem, I'm given capacitor in the problem, and I'm solving for potential. So I'm going to do 2 times the energy divided by the capacitance is going to give me my voltage squared. So I'm going to take the square root of 2 times the energy divided by the capacitance is going to give me my voltage. So that's going to be 2 times 300 joules divided by 30 times 10 to the minus 6. And when we do that, this ends up being like 4,500 volts. This is why they tell you to stay clear when you're zapping somebody. Because what they're trying to do is trigger those pacemaker muscles or those pacemaker cells to restart and put you back in sync. So that is the defibrillator problem. All right. So let's start talking about current and resistance and what's happening. So if you recall, we'll start with the periodic table. Now everybody knows it's a sesquicentennial of the periodic table. So I got my basic periodic table. Over here, if we do our little zigzaggy thing over here, these are our nonmetals. These are our metals. And if we really go into our periodic table and we look at our periodic table, this part of the table are our s orbitals. This part of the table are our d orbitals. Our p orbitals, sorry, our p orbitals, and these are our d orbitals. And then our lanthanide and actinide series down here at the bottom, those are our f orbitals. Those are the really weird ones. This s and p give us our octets, right? They gave us our octet rules. And for most of the time, that's what we play with. And we talk about ionic bonding, and we talk about covalent bonding, and we talk that these things help drive our chemistry. But then there's this big part of the periodic table that we dealt with, and we bring it up in Chem 1, and we just talk about the fact that this is metallic bonding. And if you look in whatever chem book that we've been using, because I've used 3 since I've been here, whatever chem book we've been using, basically what happens is I've got my nucleus surrounded by a big bubble of electrons, and my metallic bonding is that these metals are actually sharing a whole lot of electrons. So I like to refer to this as electron soup, because these electrons are there, they're on outside rings, they're easy to get to, the electrons can move around, which is why a lot of these things will have a +3, a +4, a +5. We'll start out with a +2. We can even have a +6. If I look at chromium, chromium can have a +6. They give up those electrons on those outer shells really, really easily. And that's why you'll get a variety of oxidation states for the electrons in this part of the periodic table. So one of the things that we know about metals, and if we talk about characteristics of metals, remember metals, those were going to be things, and one of the things is that these are good conductors. And it's both conductors of heat and electricity. So if we looked in our chemistry book, we would see that those things are out there, and we have really good conductors of electricity, and the reason is because we can move the electrons around fairly easily. And that's really what our situation is. So if we go back to the microscopic view of things, and this is really sub-microscopic view of things. So we're going to play Miss Frizzle from the Magic School Bus. And we all know that Miss Frizzle, she ended up always shrinking everybody down so we could actually look at what's happening, right? So we could actually see what's happening. If I've got a copper wire or a silver wire or some good metal that's a good conductor, copper and silver are very, very good conductors, what happens is I can actually see these electrons colliding with each other. So we've got a lot of electrons in our wire that are free to move about. And these electrons can move about in a variety of ways, okay? They can go in any different direction, but what we end up with is if I've got, and we've all done this, right? So if I'm at the subway station, and I've got a crowd of people, and we've got a potential across here that we're creating that electric field, and in our case, if it's trying to get on a subway train, right? If I've got my electric field, we're pushing these electrons in one direction. And so what's going to happen is if we use that old Newton's cradle example, if I've got an electron over here and it's going to bump an electron over here, which bumps another electron over here, which bumps another electron over there, ultimately we get an electron that pops out. So we get a series of collisions that causes the electron to pop out the other side. Now, if we name this one Fred, it's not Fred that pops out on the other side. Could be Joe, could be Sarah, it could be something else, but the actual electron that pops out on the other side isn't the one that we started the chain reaction with. But what happens is, and what we can think about is we can think about this as a flow of electrons. If I have an electric field that's causing those electrons to move, it's going to look, if I'm standing here, it's going to look like the electrons are flowing through the wire. I mean, that's the net result. It's not like water, but we can use the water analogy a lot. And we actually think about the water analogy about how electrons are going to flow through a wire because it's an easy picture for us to think about. So we know, we actually looks like our electrons are flowing. So if I'm looking at it as my electrons are flowing, and we know what's really physically happening is we got a whole bunch of collisions, which is what's going to start part of that description in the text. If I've got my wire, and I'm still playing Miss Frizzle here, looking at an arbitrary area of my wire, we can see that the electrons are moving through this area. And if I'm looking at them as electrons, we can look at it as a change in charge with respect to time. Now, this is all into account of the fact that I've got an electric field that's generating or causing the movement to happen. Now, remember, the really lousy thing is these are electrons that are moving, and Ben Franklin thought it was the positive charge that was moving. So things are backwards. Physically, things are backwards, but when we talk about current, we're looking at it from a positive aspect, even though we know it's the electron that's moving. So just kind of remember that that's what we've got. So this flow, if I'm sitting here and I'm looking at this cross-sectional area, and I can see how much charge is going through that cross-sectional area in any given time, we're going to define that as current. So we're going to use an I, and this is going to be current. And the average current for my my situation is going to be the change in charge that goes through there with respect to the change in time. I can have an instantaneous current as well. You know, as we get, that time gets smaller and smaller and smaller and smaller, I can get that particular aspect of it. Now, your book talks about, and this is one of those things that we're going to look at just to get us to where we are. You have a couple of homework problems associated with it, but it's trying to understand the concept of where we're headed, which is resistance. So if I'm looking at this and I'm looking at my cross-sectional area, we can look at something that we call, and we're going to use the letter J for it, something that we call current density. And that's going to equal the current per unit area. Now, the reason we talk about current density is if I've got copper here, which is a really, really good conductor, we know if we go to the periodic table, copper has, since I cannot remember the atomic number of copper, but we do know one thing about copper. If I look on my periodic table, because this is one of those nice little fun things, right, is that it's, we start with copper, and we could go to silver, and then it goes to gold. And it's in that same column on the periodic table. It's also in that section of the periodic table where there's 9 of them, and nickel is in there, and I think iron's in there, because they all behave very, very well, and they're like our best conductors. And I'm sure you're all wondering how on earth I can remember that it's copper, silver, and gold, and not remember the atomic numbers. There's an experiment that you take a penny, and it's what they call it an alchemist experiment. That you take a penny, and you can do a really quick chemical reaction that changes the penny from the copper color of the penny to a silvery color. Turns out it's zinc. It's a zinc coating that you put on the penny, and then you heat it up, and it turns a goldish color. Well, copper and zinc make bronze, and so it's a penny that goes from copper color to silver color to gold color, and it's just a fun little experiment that you can do. It's a really cool little experiment, cool demonstration, but it really is going copper, and then you're doing a zinc coating, and the heat creates bronze. So that's what you end up with, but it allows you, but that's why I can remember that particular column. But we know from copper is going to have fewer electrons than gold, because we've gone down a row on the periodic table, which has fewer electrons than silver, which has fewer electrons than gold. And if I'm looking at how many electrons are available to go through this area, the current density for copper is going to be different than the current density for silver, which is going to be different than the current density for gold. And that's going to lead to a property that we call resistance. Okay, if that's where we're ultimately headed, it's how can these electrons, if I'm dealing with collisions, how are those electrons going to be able to, how easily are they going to be able to move through the material, if we look at it from that perspective. So let's do just a real quick kind of derivation here, because you do have like two homework assignments that are, two homework problems that are like that. So if I do, from our viewpoint, charge is going to be the number of charges, number of little charges that go through the current. And it's going to be related to, if I'm looking at this little sliver here that I have, I can look at the area times my little width here. So that's going to give me, so to get the charges, it's going to be the number of charges in the area with my thickness, or in my volume. This is the number of charges in the volume. And now if I look at it with respect to time, and I'm looking at it for current, my charge is going to look like the number of charges times the area, and remember the change in x is going to equal the velocity with respect to time, or this with respect to time. So my change in x is going to equal my change in velocity times time. So I can put that in here as the change in velocity, change in time. So this kind of gives us a chance for flow. And so our current density is going to equal the current per unit area, which is going to be our charge divided by the unit time, which now looks like the number of charges, Q, number of charges, area, velocity, times time, change in time divided by, and this is area, sorry, left out my area, change in time. Change in times cancels, area cancels, and it's going to be the number of charges times the velocity. And this velocity we refer to as what is known as a drift velocity. And that's that net flow of the charges, how fast are those charges moving through that area. And that comes back with what material am I in. Copper's going to have a different number of charges than gold, than silver, than nickel, than iron. It's going to have a different piece. So this gets us to our good old buddy, which you guys have done Ohm's law in the lab. You've done some stuff with Ohm's law. Our good old buddy Ohm, and it's Gregor Ohm. You know, that's good old Ohm. He noted that the current density, this current density is going to be related to my electric field that I have in there, and depending on the type of material, he put in this lovely little symbol there, which is related to conductivity. And this is a property of the material. How easily is it to have those electrons do the little collision thing and have them pop out the other side? So we go through this analysis to get us to this thing called conductivity, which is something we can measure, okay? It's something we can measure. It's proportional to the field. And we now can look at it from a different aspect. So this gives us our current density to conductivity that lets us go there. Now, if I have a wire, and I can apply the electric field to it, the change in potential, now this V is not velocity, this is potential. The change in potential is equal to the electric field times the length. which is kind of what we were seeing in conductivity. Remember, I could do something across the aspect. And so this thing means if I solve for electric field, this is going to be my length divided by the potential. And now I can take my current density, and there's my conductivity, which is material related. These things are in tables. I've always said indentured servitude is alive and well. It's called graduate school. There's some poor soul out there that's measuring conductivities for various materials all day, every day. And those are in tables. And I can replace that E, so there was our E, so I can replace that with the length. Did I do something wrong? Oh, I did. That's my equation. That's V divided by L. Because all I'm doing over here is divided by L, so I'm going, wait a second, something's funky. So I got V divided by L, and we already knew that my current density is the current divided by area. Okay, I've got current divided by area. So now I can rewrite this and get rid of charge density or current density, because that's something we don't necessarily work with. I can get rid of that, and I can get my conductivity, my potential area is equal to current or length area. So I can look at the potential is going to equal current, length, conductivity, area. And now let's look at this. This is something we can measure. Turns out we can measure current, but this right here, that's going to depend on the length of the wire and the type of material that I have. So this is the type of material, and this is the configuration of the material. How long is it to what area is it? So if I go to a catalog and I look at wires, it's going to tell me, it usually gives me something per unit length, and then it also tells me the diameter of the wire. And the reason is because this thing is material dependent, and it's related to how I put my system together. So what we can do is we can define, or if I can look at it a different way, and let's look at it from a mathematical perspective, what this is saying is that voltage is directly proportional to current. And there's some type of constant here, which we've just shown is material dependent. So if I do look at that and I say, all right, let's do voltage divided by current, that's going to equal some constant. I can define that constant, and we define it with an R. And we can define that constant as with an R, and this is resistance. That's resistance. So we've gone from current density to resistance. And this gives us what we talk about as Ohm's law. And Ohm's law is that potential is equal to current times resistance. That's usually how we write it. And we've lied to you again. Ohm's law only applies to something we refer to as ohmic materials. Not all materials obey Ohm's law. A lot of them do, and a lot of them do over certain regions. So ohmic materials are, and things like copper and silver and gold and nickel and iron and all of those things, they're all ohmic materials. But when we start dealing with semiconductors and we start dealing with polymers and we start dealing with a lot of other things, they're not necessarily ohmic materials. So this only applies to ohmic materials. And it's kind of like Hooke's law. Remember, Hooke's law only applies to springs over a certain region, because we know we can take that spring and I can pull it and ultimately deform it, and it's not going to come back per Hooke's law. So we have regions where things behave like Hooke's law, but we have other regions that go in for different pieces. So Ohm's law only works for ohmic materials, but when Ohm was doing this was the easiest thing that we had and where we could look at it. So what this is telling us, based off of these are material dependent or dependent, is that I have a conductivity, and things with a high conductivity like copper are going to have low resistance. So if that number's high, this number gets small, it's going to have low resistance. Okay? It's going to have low resistance. If I have something like materials with a low conductivity, like let's take aluminum. Aluminum can still conduct, but it's not as good as copper. It's going to have a higher resistance, because the lower this number, the higher this number is going to be. So we end up with those pieces. So now I can go back and we look at resistance from a materials point of view is going to equal our length, resistivity, or conductivity times the area. And what it turns out is this and this, the length and the area, are dependent on my actual physical configuration of my wire. It's actually dependent on my wire. We define something as 1 over the conductivity as another value that we call, it's a rho, and we call this resistivity. And resistivity is usually going to be measured in ohms per meter. Because let's look at what's happened here. If I have this, if I'm going voltage is equal to I, is that right? Voltage is equal, that might not be correct. No, it's ohm meters, sorry. Ohm meters. Because I want to be in ohms when I do my resistance, because I want resistance to be in ohms. But I end up with length per unit area and my resistivity. So if I do resistivity times length divided by area, I have to be in ohms, meters, because area is in meters squared, so I can get those cancel out. And area for a wire, just so you can look at it from a different perspective, area from a wire is going to be pi r squared, where r is the radius of the wire. So to make an easy resistor, if you know your material, you can cut it for whatever length that you want it in order to get the resistance that you want. And you can already get the resistance. And resistivity and conductivity are usually found in tables. And I think it's around chapter 20, I don't remember which book I've got this one in. So there's a table in this chapter that's going to have those, and watch and pay attention to the units. Because the table, it may give you units and it may tell you up in the title. So what will happen in your tables will look like this. So it will give you a table that'll say copper. It'll tell you like something that's a nickel gold. And it'll give you resistivity. It'll give you conductivity. Be a nice meter, conductivity. But resistivity for copper is something like 1.7. and this will be like 33.0, but at the top, it's going to tell you times 10 to the minus 8 ohm meters. So if I just plug in the 33 in my calculation to get that resistivity, I'm not going to get the correct answer on WebAssign, because I have to go back to the top of the table to see the actual units that are in the table. And conductivity will be the same. It'll give you those units, and it'll give you something different. So we've got Ohm's law, which is V is equal to IR. We can go back and look at power, just like we did with our capacitors. And if I go in and look at power, power is going to be in watts, which are joule seconds. What? Power watts. And so to remind everybody, because our units have gotten screwy, current is an ampere, I didn't define that, is coulombs per second. And remember, we defined current as the change in charge with respect to time. So there's where we get those units. And we use that as an A, capital A. So A gets a little confusing in here where I'm using it as a current or I'm using it as area. But there's amperes. Volts, if we remember, are joule coulombs. Volts are joule coulombs. Power is going to equal current times volts, which is going to give me a coulomb second, joule coulomb, which gives me joule seconds. So we can look at those units and get where we're at. So power, I'm going to start out with power. Power is going to equal current times voltage. I can go in, and if I got V is equal to IR, I can replace for the I, or the V, sorry. And that's going to give me I squared R. I can replace for current. Okay, so current is going to equal V over R. So if I do this, I'm going to have V over R times V, which is going to give me V squared over R. So just like I'd had with power and energy with capacitors, I'm going to have multiple versions of the formula that I might need to be using depending on the situation. So now let's look at something real quick. Let's do a practical problem. And for those of you who live in older houses, reading the power requirements, and this time of year it's entertaining, reading the power requirements on our pieces of things like, so if I have a space heater, so let's go, what is the current required by and it turns out my space heaters usually are about 1,500 watts. Okay, my space heaters with 1,500 watts, and we're going to use, it's going to have a resistance heater in it. And we're going to say it's 12 ohms. I want to know the current that's required. Because if I go in my house, my breakers are usually set at 15 amps. That's a standard breaker. Okay, so if I do that, power is going to equal I squared R, because we just did that. So power is going to be divided by R is going to give me I squared. So if I put in my 1500 watts divided by my 12 ohms, and that's not the problem I put in my notes, so that's why we have to get the calculator out. That's 125, but that's squared, that's I squared. So this is 125 amps squared. And this is where, like I warned you, that my unit analysis gets a little funky because I have to go back and remember everything. But that's amps squared, so if I take the square root, that's going to equal 11.18 amps. Or that's going to equal 11 amps. So if I have 11 amps, so I have a space heater on my circuit. And if it's running, and it's running full out, it's going to take 11 amps of current. So I've got my space heater in my bathroom to keep my water pipes from freezing up, right? Because we've had a wonderful time. So I got that right there, okay? Got that right there. So there's my amps. And now I'm plugging in a hairdryer. And common hair dryers are 1,000 watts with a 12 ohm resistor in there. So if I do that one, I get my power divided by R is going to give me my current. It's going to equal my current squared. So that's going to be 1,000 divided by 12, which is going to give me, this one I do have in my notes. Gives me the square root of 83.3, and that works out for current to be 9 amps. If that's 11 amps, and that's 9 amps, and I have a 15 amp breaker, guess what happens? The breaker switches off in order to protect your circuit. Some houses have 20 amp breakers. Some houses have 15 amp breakers. Some houses only have 10 amp breakers. So my little resistance heater is not going to work so good on a 10 amp breaker. So I can't put 2 resistance heaters on my circuit. So we have issue. All right. So last year in Ponca, in January, which it's going to be this month in Ponca because we've been at 9 degrees, right? Let's look at, I have a 1,500 watt resistant heater. Those are my little, that's my little heater that I got plugged in. Somewhere along the line, we talked about that energy was in joules, right? And we just did it just 2 seconds ago. We said that watts are joule seconds. Okay? So if I do watts times seconds, that's going to give me energy. So on my electric bill, having a kilowatt hour is if I do the conversions, I'm going to relate it back to energy, right? I'm going to rerate it back to energy. So kilowatt hours are energy. So if I'm running my little resistance heater, and most of us have been running our resistance heaters, if we have resistance heaters, right? For the last, since about Friday, or what, Saturday is when it started getting cold. So let's say from Saturday morning to right now. So that's Saturday, Sunday, Monday, Tuesday. That's 4 days, right? So that's 4 days. And 4 days times 24 hours per day. That gives me 96 hours. So we've been running a 1500 watt resistance heater for 96 hours. So what I do is I take my watts times my 96 hours there. So I get 96 times my 1500 watts. I've used 144,000 watt hours. So I'm going to do it as kilowatts. So I'm going to divide by 1,000. That gives me 144 kilowatt hours. And if I'm running at an average of 15 cents per kilowatt hour, it's cost me $21.60 to operate my little resistance heater to keep my bathroom warm so I don't freeze my pipes. So today you got practical physics. You get practical physics. So if your house is running on an electric heat, you're using resistance heating, and that's how you're keeping things warm. That's why your electric bill goes so high in the wintertime, because you're using that to generate the heat. So it's a big user, it's a big drain. Okay. So I'm going to do a problem in the homework so that you guys can see how some of these drift velocity things work. So there might be a problem that says something to the effect of that I've got a drift velocity of the free electrons. And this is in copper, 7.84 times 10 to the minus 4 meters per second. We want to calculate what is the electric field in the conductor. Okay, what's the electric field in the conductor? So if we're looking at this, we've got a couple of things that we want to look at. Just remember that force is equal to mass times acceleration, and that acceleration is equal to force divided by the mass, which if we go back, that's QE divided by the mass. But I can find acceleration if I remember my kinematics. So I can do so I've got that substitute in there, so I get E, Q, M, T. Now if I'm doing drift velocity, we can make an assumption that my initial velocity is 0. And this T, if I'm doing drift velocity, that T becomes the average time between collisions. And that we use as a little tau. So that's the average time between collisions. So my average drift velocity is going to equal the number of charges, the electric field, mass, divided by tau. And this is also dependent on the material, and it's the size of the atoms. And the number of electrons per unit volume. So this is related to physical properties of what I have to deal with. So I can go back and look at current. Okay, I can go back and look at current. And we can play with to find this tau. So you can go back and say that current is equal to NQ velocity, like that right there. And we now know what velocity is, so I can go back in and put in that NQ squared E M tau. And it turns out that conductivity is equal to NQ squared tau mass of the electron, or resistivity is equal to ME NQ squared tau down here, because conductivity is 1 over the resistivity. So I can look up copper, since it told me copper. I can look up copper, and that's 1.7 times 10 to the minus 8 ohm meters. So I can actually plug in some numbers. My drift velocity ultimately equals this resistivity Q times the number of electrons per unit volume. We also find that N is equal to Avogadro's number, the molar mass of what I'm dealing with times its resistivity. So we can calculate N, and if I do N for copper, oh, and this is density. This is not resistivity. This one's density. That's why these things get confusing. So N will equal 6.02 times 10 to the 23rd. And I get, and you can look up density of copper, and that's this, and that's kilograms per meter cubed, divided by 0.0635 kilograms per mole. And that gives me a number 8.46 times 10 to the 28, 1 over meters cubed. And if I rearrange this all stuff back here, E equals the drift velocity, the resistivity, the charge, and the number of electrons. We were given the drift velocity in the problem, 7.84 times 10 to the minus 4. Resistivity we get from a table, 8.46 times 10. This is the N, sorry, that's the N. This is velocity, that's N. 28, 1 over meters cubed times 1.6 times 10 to the minus 19 coulombs. This is charge. And it's 7.84. Oh, that's because that number. oh, we want this number. 1.7 times 10 to the minus 8 ohm meters. And when I plug all that into the calculator, it's going to give me 0.18 volt meters. Now, because most of you are not going towards electricity stuff, knowing the actual electric field in a wire is not something you have to do. I have homework problems there so that you can see it, but the odds of me giving you a question on a test that looks like this, slim and none. Odds of a question that look more like, I have a resistance heater and I need to know how much energy that it used. Yes. Questions like, what is the power requirement, or what is the voltage requirement, or something, or the current requirement for my resistance heater? Yes. Am I worried about the electric field in a wire? No. But you do have homework problems on it, just to get you exposed to it. But why do we do care? It's for things like this. We want to fabricate a wire from 1 gram of copper, and it has to have a resistance of 0.5 ohms. We want to know the length and the diameter. We know the length and the diameter. So resistance is equal to resistivity times the length divided by the area. And we know that area is going to be, length is going to be pi r squared. R is equal to the diameter divided by 2. So if I'm going to go in here, I'm going to get R, L, pi, D divided by 2 squared. So this will now be 4 resistance L pi D squared. We can look up resistivity of copper, which is 1.7 times 10 to the minus 8. The density of copper, because we might need it, is equal to 8,920 kilograms per meter cubed. We can find L over A, if we need, which is resistance divided by resistivity, 0.5 divided by 1.7 times 10 to the minus, oh, that's not 8, that's 8, not 18, sorry, minus 8. That gives me 2.94 times 10 to the 7th, 1 over meters. Because resistance, this is in ohms, this is in ohm meters, ohms cancel, so it's a 1 over meters. Density is equal to mass per unit volume. Volume is length times area. So I can do density is equal to mass divided by length times area. If I'm looking for area, that's going to be mass divided by the density times the length. And density times length. And length is going to equal mass divided by density times area. If I'm solving for L first, I get L times dl over m, because this is equal to L divided by A, and that equals 2.94 times 10 to the 7th, 1 over meters. This gives me L squared is equal to the mass divided by density times 2.94 times 10 to the 7th. And we were given 1 gram, so it's 1.001 kilograms. Density is 8920 kilograms meters cubed times 2.94 times 10 to the 7th, 1 over meters. This gives me 3.3 meters squared, which gives me the length is equal to 1.8 meters. And you can do a similar analysis, and you'll end up getting a diameter of 0.28 millimeters. Okay, I gotta cover one more thing, and then we'll call it quits for the day. Reason we use resistance heaters, besides the fact that, so if I'm thinking of a good old light bulb, right? These are the old kind of light bulbs. In the old kind of light bulb, it had a filament in here. And when we heated up the filament, it glowed. So if I have an electric range with the coil on it, all that is a big resistor that's going to heat up with current in the resistor. And it turns out that the higher, depending on which kind of material I have, the higher the temperature, the higher the resistance. So there is a temperature dependence on this resistance. And the temperature dependence goes like this. The resistance is going to equal the resistance of the material, 1 plus its temperature coefficient alpha times its change in temperature. So for copper wire, alpha is 3.9 times 10 to the minus 3, 1 over degrees C. And this is the temperature coefficient. So I can actually calculate the resistance, the new resistance, depending upon how hot my wire gets, because that's going to change the properties of the material. And you've got a couple of problems that deal with the change in resistance that's out there. Okay, so I've already done power requirements, already done a couple of others. So I'm going to stop there, and we're going to dive into new stuff on Friday, and we keep going. You guys good over there?